let's start this. A couple of terminology, and then I'm going to dive into the discussion. So anything that is out of norm that we see during inspection, we call it anomaly. But this is not a term that we typically use. If something happens during inspection after manufacturing, we call it flaw. And if it happens after service, we call it damage, like impact damage, for example. And then a defect, which is typically used quite often. So people mistake all of these terminologies. The last two terminologies are typically what people use: manufacturing flaw, service damages, and then defect is if any of those flaws or damages go beyond the threshold. For example, porosity. If the cross-section of a material has more than 2% surface area porosity, we call that a defect, because then it's beyond the threshold set in aerospace industry. It's not fly-worthy. They have to throw it out and start over. So 2% is a threshold. For space applications, it's 1%. So all the black areas that you see, those are voids. This cross-section, I did it with image J. I think this one had 7 or 8% void. It was intentional. We wanted to have something with lots of voids to do cross-sectioning. But there are other types of damages and defects. I have some samples I'll show you as I go through this, and feel free to ask questions as we do this. Some of the things that might happen are just purely cosmetic, but then in some industries, it's quite challenging to get rid of them. So I'll explain to you the samples that you're going to see in a bit. Some of those things are surface damages and surface defects. I have some samples here I'll pass around for people who don't see them on Zoom. So these are made using infusion process, where you have a bunch of glass fibers. I think these were 8 layers of glass fibers. And then so you put it inside a vacuum bag and you inject resin from one side and just slowly goes through this. And then we stop the process at the end, so you can see the dried section at the end. This was part of the projects I was doing myself to create transparent composite. Unintentional outcome of that project for me was that I could see the defects quite clearly that you typically can't see if you have carbon fiber. So this one that I'm going to pass you around, look at the surface, and you see a pattern on the surface. We call this orange peel pattern. And this is quite, let's say, unacceptable defect if you're making high-end luxury cars, for example, or if you're making boats, that the surface finish is quite important. So orange peel is part of the defect. It happens because the resin shrinks, and then you will have that type of defect. So you have to mitigate that. Other types of defect that I'll show you, some of them external, some of them internal. Micro cracks is one of those things that might happen internally. So why would you have micro cracks? Of course, it could be loads, but you make this composite at elevated temperatures, like 350F, 400F, and then you cool it down. As you cool it down, resin shrinks, fiber doesn't shrink, so you create residual stress in some of the layers. And if it's too much residual stress, you will get micro crack. For space application, if you send spacecrafts out to orbit, the temperature drops to, I don't know, cryogenic temperatures, then it becomes quite intense. You will get lots of micro cracks. So another sample I've got to pass around. This one has some, was it this one? Yeah, so this one has some white spot in it. If you look under microscope at that white spot, those are fibers breaking the resin coming out of it. So it's a micro crack. And this happened quite interestingly. When the manufacturing was done, this was without any defects. I don't know if people can see this. After 2 weeks in ambient condition, the cracks started appearing. And probably because of moisture absorption. Moisture goes in, expands, and then extra stresses are applied on the material. So you get those white spots. Those are micro cracks, if you could see them under microscope. So what are common things that you might see during manufacturing? Delamination is a big thing. If you have sandwich panels, you have core response, for example. If you have a solid laminates, you might have delamination. Some of the delamination happens because you have weak bonds, kissing bonds, as we call it. But some of it might be because you're doing drilling. It's a curved geometry, too much out of plane stress. At the end of the process, you will get some defects that are not acceptable, perhaps. Void and porosity, people, again, mistake them. Void is any area where there is no resin or fiber, like the black, black areas. When you combine them and create like a percentage area, that's called porosity. So porosity is basically you add up all the voids. I have another sample that I pass around. Two samples I have. And both of them have, maybe this one, both of them have porosity. I don't know if people can see it, but you can kind of see that it's clustering on the other side. These white areas are not microcracks now. Here you can see larger porosity. Here you can see larger voids, smaller voids. Again, unintentional outcome of making transparent composites that you can see all of these defects quite clearly now. By the way, any questions so far? If I'm going too fast? No? So this last one has become quite critical in recent years. Inclusions, sometimes called foreign object debris or FOD. And you've probably heard it or might not have heard it in the news. That has become quite a hot issue for Boeing, for example. So that type of object that you leave inside the material is cause of concern. Did I tell you about the story that some of these are intentional? I probably didn't tell you. When people realize that, they were making this aircraft and they will, sometimes they would see patterns, like circular patterns, the size of a coin inside this composite part, like a wing or what. And if you see it in ultrasound, that's a big defect. You have to see why do you have that. It's not like a small void of porosity. It turns out that in some of these aircraft, the workers put in a lucky coin in the middle of the layout. And they can say, oh, this aircraft that flies has my coin in it. So that was prevented. That was one thing. In some other inspection, people realized that there is a rectangular section that appears in some of the ultrasounds. And when you're making this composites, typically you have this in the past, maybe they do have now, they have this printed sheets with instruction, and sometimes the worker would left them inside the layup. It's paper. It basically burns and it becomes like a rectangular defected area. Then you have to throw out that $1 million wing because of a piece of paper at the end. Okay, so surface porosity, you might see it, you probably can't see it in some of those samples, but it might be in some of those samples that there's some areas on the surface that doesn't have resin. So you can actually see dry fibers under it. And I remember 10 years ago, the hot topic for Boeing was surface porosity. Everyone was concerned about surface porosity. They didn't know why they have surface porosity. Sometimes they had it, sometimes they didn't have it. One thing that turns out is that if you are making things on composite tools, you will get a lot more surface porosity than in-bar tools. So that was one observation. Then they realized that when they have composite tools, the tool itself absorbs moisture because it's composite. You go into production, the moisture during processing comes out of the tool, accumulated in the surface between the composite part and the tool, and creates this void. That was one of the key messages from some of them. There were other things. It could be like an indication there are also porosity in the bulk, but moisture has a lot to do with the surface porosity types. There could be effective impacts. There could be effective, the things that you start seeing, that you start playing with the fibers. For example, wrinkling. I have a sample I'll pass around in a second. Especially in corners where there's mismatch of geometry, like the outer layer has one radius, the inner layer has another radius, so there's a mismatch of geometry. That excess length goes somewhere in the shape of wrinkling. You might have areas where there is resin, but there is no fiber in it, resin-rich areas. When you're doing automated fiber placement and there's gaps between the layers, and you will end up with that. And sometimes this leads to dimensional changes, unintentional. So another sample I'll pass around. You can see, by the way, that in the quality of the panels I was making, it's becoming better and better. In this one that it goes around, what do you see? Do you see dimensional changes? So this was supposed to be a flat part, but it's not. The reason is that during manufacturing, the heating was not controlled. So it was going one side earlier than the other side. So a non-uniform heating. So you basically create residual stress one side, and the other side, they fight and it bends. The other thing that you'll see is you'll see these patterns. It's like a wave on the surface. Those are wrinkles. They were excess length. So you place them in a tool, and then you apply pressure, and then excess length goes somewhere. And in this case, went out of plane or wave in a spin plane. Questions so far about the samples that went around? Everything is clear?
I guess this thought is not fully formed, but looking at that panel, the way that it's deformed reminds me of in woodworking. If you have a plank that's straight and you cut it length or like along the length, sometimes you'll get a similar thing because the wood has internal stresses, and when you split it, those stresses.
Yeah.
I'm wondering if there are ways in woodworking to avoid that, and I'm wondering what the ways.
Yeah, so you're right. So there's residual stresses, and sometimes when you're doing drilling or cutting, this also happens in composite, that you're releasing some of those stresses, then you will get warp samples. In this case, it was not because of that, but it could be another contributor. Asymmetry of the layup, asymmetry of the heating condition, all of that may lead to deformation, but some of it's just because they're two dissimilar materials, resin and fiber, and they fight residual stress deformation. So you can mitigate part of that, not all of it. But there is a threshold. If your sample has beyond a certain threshold, deformation is unacceptable. Because when you go to assembly, you have to force it to be flat or force it to fit into a corner, and that increases residual stresses. Actually, if you go back to news and check, there was that problem happened for 787. There were 18 787 that FAA basically banned to fly, and they were doing some investigation. They mentioned mismatch of geometries, things like that. It was exactly because of this. They made the parts, the mismatch was so far, they did the assembly anyway. And that being is under a lot of stress because of that dimensional changes. So drilling of composite in general is very difficult. You drill into the composite parts. When it exists the other side, you might get delamination. These are layered materials. So that's one problem. You might create a scenario where you're breaking the fibers. You might burn the resin because the temperature goes high. But all of that, you can probably come up with methods to mitigate. Design the drilling parameters, design a specialized drilling bits, which people do, control the speed and temperature, all of that. I've heard the most difficult thing is stack drilling. You have a composite part sitting on top of an in-bar part or aluminum part, and you want to drill through them. So the composite part needs its own drill bits, its own drilling parameters. The aluminum or in-bar has a different parameters. From what I know is that they have to drill all the way to the boundary, take it out, change the drill bits, and change the parameters, and then drill into the metal to make sure they have proper drilling scenario. So it's a challenge, and but we have some let's say empirical rules to take care of that at the moment. Another problem that might not seem quite obvious, CRN is, by the way, the center I was working at Canada before, Composite Research Network. So this is from that area. So when you're making thermoset composites, it goes into polymerization. It creates a network, a cross-link network. And if the cross-link is not properly done, is undercured, then all the properties of the material gets affected. For example, it's glass transient temperature, it's stiffness, So this is one of those issues that is really difficult to detect as well. Ultrasound can't see polymerization. Most methods that we have typically just look at the surface, like FTIR or other methods. So you really can't look into the bulk of the material unless you cut a corner and then take it to the lab and do this basically destructive tests. The non-destructive tests, we don't have anything proper, unfortunately. So you have to make sure that you don't get into this scenario. I'm going to talk about that when we get to the repair section. I'm going to address this. So before going to the next section, if you're wondering, finally, I was successful. I made part without any defects. So it became completely transparent. So this one also has 8 layers of glass fiber inside. We modified the refractive index of the resin with additives, so they will have the same properties of glass, and it becomes a transparent composite. And then you have to remove all the defects, the voids, and then the micro cracks, and then the orange peel, and all of those things to get to this point. And then no one bought it from us, so. Yes.
Ask about that, because I know like one thing about glass is that it can let heat through really easily. And so like, if you want to insulate a house, people are looking like different ways to do that.
Right,
Could
right.
that be an application for this?
So you're reading we had a patent. The patent was that now that it's strong, you get 2 of these, and then in between them, you create a vacuum, and nothing goes through the vacuum, right? But it was too expensive, and no one wants it.
Few $1,000s.
Yeah. So we went into a different direction. I brought this just as an example. We thought maybe some art pieces. So we could print on glass fibers with a printer, and then you could do the manufacturing. You could embed patterns inside composites. Again, no one bought it from us. So these 2 have lots of defects, by the way. That was a failed attempt from 10 years ago.
I have one other question.
Yeah.
For like the 787 or other airplanes, drilling a hole in the fuselage to put a window in creates a weak spot. I'm wondering if there's a way that you could like integrate a clear, transparent section so that you don't have to introduce.
Right. So I think we also had that idea at the time we were thinking about that. There was another company that they could control the transparency, and that's what 787 now has. Right. So it's. Yeah, it's a much better thing to have than strengths. Yeah. Okay, so move on. So now you have defects. First of all, how do you see it? So we're going to talk about destructive. So we talked about destructive testing before. I'm going to talk about non-destructive testing mostly now. But you can do destructive tests, but you cannot do destructive tests on, let's say, a wing of an aircraft. But you have other ways to do it. During manufacturing, typically you make the part a bit longer. Then you cut the corner and you do tests on them. You make what is called traveler's coupons. You're making a wing and you're also making a small panel in the corner. And then you will take that and do tests on that. So it's not the same part, but it's a traveler coupon, as they call it. Or you make sacrificial parts just for destructive testing. And typically you do that. You make like a wing at the beginning and you cut it, and then you do lots of tests, tons of tests, and you quantify it. So you can do all of these things. But let's not talk about destructive tests. Let's talk about non-destructive tests. There are tons of non-destructive tests. Some of them are good for some type of defects. Some of them are good for more types of defects. And some of them are not good at all, or not used typically. So some of them I'm going to go through, and you can see that you don't need to memorize this. Just to know that for every type of defect, there is a better way, or there's a best way. And then you have to employ different testing methods when you're considering different types of defects. So I'm going to discuss some aspects, some of the complexities there. Any more ideas about transparent composite, let me know. We had, eventually that no one bought it, we wrote a paper and we published the way we made transparent composites. There's a paper I have in Composite Science Technology. You can go and look at how we are actually eliminating all the defects one by one. Okay, so the first thing is called tap testing. Sort of like low-end approach is that you take a coin and you tap on a surface. In the areas that you have delamination, the sound is different than the areas that don't have delamination. So that's the underlying idea. And some people actually have some specific hammers that some of those maintenance crew that they use it when they suspect that there's defects in some areas, but there's a better way of doing it. And those are like more automated ways. So I think this is the hammer that people have. In the automated way, there is a system that taps an area with a frequency. And these are like sonic waves. So you can actually hear the tap. And then it records the sound. So you will map the entire area and you will get like a map of this. So it actually records the sounds coming back. If you know an area is good, you can compare. So you might have like a good sample, you calibrate it on a good sample, then you go to an aircraft and this equipment taps on the surface and then it creates this color map. So you will figure out, oh, there might be something in an area because it's too different from my sample. Then you can go and do more expensive inspection like ultrasound. But this would be like a very cheap way to like quickly get some insight. But since it's sonic waves, it cannot detect small defects. It can only detect large defects. So that comes here. So think about the frequency of sound waves. We can hear anything between 20 hertz to 20 kilohertz. Actually, male and female have different capabilities. I think male can hear up to 16 kilohertz, and then the female can hear up to 20 kilohertz. But beyond that, it's we cannot hear that. So this tap test that I said generates frequency in this range. You can go all the way to 200 megahertz, and those are the frequencies that are used in some specific microscopies. We don't use that in composites. If you do medical ultrasound, baby ultrasound, it's typically 10 megahertz frequency. I'll talk about that technology because that technology has been borrowed, exactly the same technology for composites inspection now. There are some techniques that we call acoustic emission or sonic, let's say, analysis, and those are lower frequency, like 100 kilohertz, 200 kilohertz. If you are looking at porosity, small microcracks, typically the ultrasonic inspection is done in the range of, let's say, 3 to 10 megahertz. So all the equipment that you see that are used, for example, in a factory, when there's a probe goes onto a part, those are typically in this range. If you have a sandwich panel, you might have to go to lower range because sandwich panels, there is a empty core. So you want to go into lower frequency. So people who are experts in ultrasound, they know exactly to what frequency, that's one of the knobs. What frequency you have to go to inspect these types of defects on these parts. So that's the first complexity. So let's first go over some basics. Ultrasound, you have a transducer. There's a piezoelectric sensors that has a resonance frequency. So you give it a bit of power. At some specific power, start vibrating, the specific frequency. That specific frequency depends on the type of transducer. So there are tons of transducer, different shapes, different powers, and different frequency. Once they start vibrating, they create mechanical waves. So they tap on the surface really, really fast, but you can't hear it now. So a signal goes into the part, hits any voids or empty areas and comes back. If there is no defect in the part, it goes through the thickness of the part and then comes back, no problem. If there is anything, it goes and comes back earlier than expected. From that time difference, you will know that something is happening. This is called pulse echo. So this transducer sends signals, then listens, sends and listens, sends and listens. So there is intervals that is sends signals, there's intervals that is listens. So that's like the basic underlying concept. So now take this and look at these two samples. This is what we call a scan. So you will go over some defects through the thickness of the material. If there is no defect, you don't see any signals coming back. The moment you go over defects, you start seeing signals coming back. So you will interpret that something's happening in the part. So that's pulse echo. But there is another way that I've seen a lot, at least in factories, not in the lab environment, where it's called true transmission. That one probe sends a signal all the time, and the other probe listens. So one of them sends, the other one listens. And then you will interpret the same thing. It's the exact same process, but here, some cases, you have to divide the time. Send, listen, send, listen. Yes.
You also get the spike backface.
Yeah, I don't show it here, but you're right. I'll show it in another slide that you can see that, yeah, you will see the backface. Here, it's not quite clear here, but there's a defect here that you go over it. And then, so what it happens is that if there's no defect, you send the signal and the other probe sees something quite strong because it receives all the signal. If there's a defect in the middle, the signal goes, interact with the defect, and a smaller amount gets to the other probe. So from that difference, you'll say, oh, something was wrong through the thickness of the material. But we typically don't use ultrasound like this. You probably use it something like this. So there's an automated ways typically that there's like a probe goes over the entire surface, looks at all of these scans, and then reconstruct a 2D map, colored map. And the colored map represents that some areas had problems, go and check, and some areas is okay. So this colored map, we call it CS scan. And it's quite common. Every part that you make in aerospace, you have to have a CS scan with it. So all the ultrasonic inspection done in aerospace is for this purpose, to create a CS scan. Okay, questions?
Yes, I have a quick question.
First Zoom, you go ahead.
The difference between ultrasonic and pulse echo?
Right, pulse echo is a type of ultrasonic where the signal goes from one probe, hits the back of a sample and comes back. True transmission is another type of the ultrasound, when the signal goes from one probe to the other probe, both of ultrasound. Then the way you look at the data is either a scan, which is like a data point, or a better way is a CS scan where you have all the data represented in a colored map. Was that clear?
Yes, thank you.
Are the A, B, C scan, is this more reliable? Is that why they choose?
So CS scan is easier to interpret, but there's another one which is called S scan, which you're going to see, or sometimes LS scan. And that sometimes is even better than these two, if you want to look more into the details. But that requires a very specialized way of ultrasound, which I'm going to tell you, because these ways are not the way we do ultrasound for larger parts. It's too slow, let's say. So we have a better way of doing it. And it's too limited as well, say. So this is the best way of doing ultrasound. It's a system called phase array. And we didn't invent this. This was done for medical applications. This is exactly the technology when they do for baby ultrasound. So the way it works is that there is a probe. In the probe, there are multiple sensors. 16 or 32 or 64 or 128 is typically like that. And the software delays vibrating this in a way that then when the sound waves start interacting, you can focus on specific areas with very high resolution, or you can steer it. So look sideways or the other way. That's why when you look at the baby ultrasound, it's like a triangle shape, because the probe basically, the same probe scans an angle. So that's the idea of phase array. Yeah, it's like a camera. Think about it like a camera that you can actually focus, but you can also turn the camera side and look at the sideways. So there are some cases that this becomes really, really useful. For example, there's a thickness of the material, and then you have something blocking the inspection, like a stringer, and you want to look at under the stringer. So with the probe, you go close to that stringer and you look sideways using this method. Any other ways, it's not possible. This way also is the way that people inspect welding, because welding is typically, let's say, I don't know if people on Zoom can see, let's say you have a welding in an area, and then this is the welding, and you want to inspect the welding, but you want to inspect this surface or this surface. So the probe comes in here, sends the signal, hits the back wall, bounces back, looks here, and then comes back. And you can inspect some surfaces that are not the back walls, like oriented. So it becomes quite useful, the phase array approach. So everything that you see, for example, in a factory like Boeing factory, they're all phase array. None of them are single probe typically. I don't think we have phase array now at UW. I think ME department has something which is just traditional ultrasound, not phase array. This is what I call, this is called sectorial scan, that you basically, the software changes the way it fires the probes one by one, and it scans a surface, a cross section. And then you can see like voids or damages or what. Any question about phase array? Good. So some of the complexity that you might think, imagine that you have a paint layer, then which is polymer with some pigments. Then you have a metallic mesh, which is, we're going to talk about it for lightning strike protection on the surface of an aircraft. Then you have the composite part, and you want to inspect this individually. One probe doesn't work. So people who are expert, they switch the probes for every section, and they can put the result back together. It's a very, it's like an art form. That's how to select these probes, what frequency to use, what power of the probe to use, what are the delays, how to interpret the signal. It's a very complex process. They're as far as I know, they are paid a lot. People who are expert in ultrasounds, they get a lot of money. This is also an interesting approach, but I would say has very limited applicabilities. For some cases, it's good. Imagine you're inspecting a sandwich panel, and there is disc-bound delamination, a face sheet, and a honeycomb core under it. So in this method, which is called thermography method, you have heat sources and IR camera. So the heat sources heats up the surface. And if there is like a disc-bound under it, you will see a different temperature distribution. And then you can basically back calculate that to what was happening under it. I would say it has limited applicability, but having said that, there is a different application of this, which is called laser ultrasound. So this is a technique that Airbus uses exclusively. I've seen Boeing uses phase array and Airbus uses laser ultrasound. Laser ultrasound, you have laser that heats up the surface of the part, and then that heat becomes mechanical waves, goes into the part, comes back, and the vibration gets detected by the laser ultrasound. So it's instead of mechanically vibrating surface, you're using laser to vibrate the surface. Yes.
This method a lot more time consuming than ultrasound?
Yes, yes. And honestly, I haven't seen it to be used in application. So I don't know if because of time or you don't want to heat up, I don't know, the paint, for example, or what. So it might not be used it might have very limited applicability, I would say. I tried to implement it in one of the projects. It was very difficult to control the heating and then interpret the results. So I personally don't like it. X-ray inspection or CT scan, you can do it on the large parts, but you can do it on smaller coupons. So the whole idea is that, so there's this X-ray rooms that the X-ray signal comes in, and then there is a receiver that receives it, but it creates a 2D map. So if you have cracks, you can see it quite clearly with X-ray, but it's a 2D map. But there's a way to convert that into a 3D reconstruction. So there are these rotating stations, and you place your samples on top of that, and this rotates it 1 degree, and X-ray signal, 1 degree X-ray signal. So it takes 360 images, and the software reconstruct everything into a 3D view. So this is called 3D CT, or typically you do this for a very small specimen, micro CT 3D scan. I was working a bit for a while with Synchrotron in Canada, and they had a room the size of this with a huge station in the middle, which could rotate. and you had to go outside of the room because of the X-ray. So you could put things really, really large on top of the station to do X-ray. And I asked, why do you have this? What is the application? And it was used to do X-ray on horses. Like $1 billion synchrotron, there was, I don't know, but it's in Saskatoon, which there's a lot of farmers with lots of horses. So to please the local people, I used it to do aerospace composites. It's like a tiny piece on that huge station. It was rotating. Okay, I'm gonna talk about repair. So we talked about defects, inspection. The last section for today is repair. Any questions on these two sections? Everything's good? So we talked about different categories before. Let's say there's a, I'm not going through detail, but let's say you realize that you have a problem and you have to repair it. Then it has its own challenges. If it's category 1, it's fine. You don't need to do any repair. Category 2, you might be able to wait a bit and don't do substantial repair. But category 3 and 4, you have to do proper repair on an aircraft. And there is a repair manual, maintenance manual that comes with an aircraft, which if you don't have it, which if Boeing doesn't provide that, FAA doesn't certify aircraft. So you have to have that repair manual. So how do you do repair and what are the complexities with repair? There are typically, you see some repeatable steps. You have to remove a chunk of material. Then you have to create a patch of a fresh material, exactly the size of that chunk of material removed. Then you have to do a vacuum bagging and heat it up locally such that that new material cures and gets bonded to the old material. So you do this, for example, by using this heat blankets. And imagine this is the wing of an aircraft. So you can create like on the wing, you will create this vacuum envelope. And this heating blanket goes inside the vacuum envelopes and heats up that part locally. And then you will get the final repaired part. It sounds easy, but it has lots of complexity. It's not sound easy. There's lots of complexity in removing the material and then creating the patch, but in heating it up also there is lots of complexity. So what are some of the complexities? So this is a repaired part which didn't go well, but I'll explain some of the problems, why a repair might go wrong. Imagine a case that you are repairing a surface of a fuselage. So we are on the other side, the outer surface, and there's this stringers and these frames. And let's say this is the connection. This is the point that we have to do repair. So on the top surface, underneath that, we have this big frame and we have this big stringer. And this is a repair area. So what you have is a section which is quite thin, a section which is thick, and a section which is extremely thick. So you put a heat blanket on here, you heat it up. Where you have a thin part, it heats up properly, so you can heat it up to the temperature you want. But the other part, which is quite thick, it needs a lot more energy to heat up. So you'll end up with the parts that are not properly cured. But you go, let's say you go opposite way. You heat it up such that you have enough energy in these parts. Then it will be too much heat that it will burn the other side. So when you have a thin part and a thick part and you have a heat blanket, either you're gonna have a situation when you're not properly curing in one section, or you're gonna burn the other section. It's really difficult to control this. So how do we go around this problem? First of all, imagine that, so there's a machine that I'll explain to you how this machine works. You would have thermocouples that can tell you what was the temperature that you set for the machine to heat up the heat blanket. So let's say that's the green cycle, that's temperature time. And then there's thermocouples in the yellow areas. Thermocouples in those areas probably record something lower than what you set for the heat blanket. And there's this thin areas that will probably record something higher. So the thin areas would burn, the thick area would not cure properly. So as an M&P engineer, if you're in charge of the repair, the main thing you have to do is come up with a strategy for repair. So I'll tell you some of the techniques that people might use. First of all, this is, you can see the burn mark, which this was not the proper repair. So how the system works is that you have lots of thermocouples. So all these stars and like pink circles and then the yellow circles are all thermocouples, let's say. Some of the thermocouples, these are the blue stars, you put them around the patch to control the process or to see the temperature. That's how you get this map. You have thermocouples everywhere, so you can see how was the process. So around the thin section, around the thick section. Then you have other thermocouples that the machine uses them to control the power of the blanket, heat blanket. So let's say you have a thermocouple, it sends a signal back that the temperature is lower than what you want. Then the controller is going to send more power to the heat blanket. Temperature would go up. Or the thermocouple says, oh, it's too much heat. The controller will reduce the power going to the heat blanket. So it's by receiving a feedback that can control to adjust the temperature. So you have some thermocouples which are there for adjusting the temperature. The machine reads them. I'll show you the equipment that is used for this, and some for reporting. There's another way to look at the temperature distribution. It is using IR cameras, which is used a lot. So you can see the distribution. If you look closely here, this is a heat blanket, and you can kind of see like this lines. These are the resistors inside the heat blanket. So inside the heat blanket, you don't have a uniform temperature as well. There are areas which is just plastic or silicon. There's areas which is just resistors, so you will get proper heating. So that adds to the complexity when you're heating a part using that blanket. So let's say you can map the temperature. How do you come up with this strategy? That's what we are interested in. There are some strategies which might not be quite useful, but maybe sometimes. You can insulate the back of a surface if you have access to it. And sometimes that helps, sometimes not. Maybe you would use additional heat blankets in some areas. Sometimes useful, sometimes not. There's better strategies. But this could be like a cheap way of doing it. Cold plates, you can have like, if you could have like a thin layers of aluminum covering everything, the heat blanket would go on top of that, or somewhere else to use this metallic cold plates, you can somehow redistribute the heat. It's not easy, especially if you have a curved surface. So I would say these are probably less useful, but this could be one approach. What are better ways of doing it? What do you think are the better ways of doing it, by the way? How do you resolve this issue? That I want to heat this up. I have an area which is thick, an area which is thin, and my repair is right in the middle. How do you repair it such that everywhere sees uniform temperature? Yes?
Seems to me you could put more like just sacrificial material on the thin spot so that everything behind it is of uniform thickness, then you would have less of an issue with.
Yeah, so that would be the insulate. Yes, that's a way of doing it. So we'll put something in the back or like locally increases the thickness. Yes, that's one way of doing it. It's not, I would say, the best way, but because then you have to make sure the contact, if it's a curved surface, then do you have access to the back side? Maybe it's because you have always access to one side, maybe not both sides, right? But if you have access, yes, it could be a method. Any other way? Yes.
Can we have a modular type heat blanket that you can use for wires?
Yes, there's ways to do that. I'll show you one example. That's one of the ways. It adds to the cost, but sometimes that's the only way to do it for some very specific geometries. Let's go through some of the strategies that you might use. First of all, how does the equipment works? There is this suitcase, which is quite portable, and that's on purpose because you want to go somewhere and then repair parts, so it can't be like a huge equipment you're moving around. This suitcase has ports for vacuum, so you can create a vacuum and it knows when to apply the vacuum, how much vacuum it applies. Then it has a bunch of connection points for thermocouples, and those thermocouples would go inside a vacuum part to either control the temperature or to control the power. So the signal comes back, and then this suitcase basically controls the power going into the heat blanket. Heat blanket gets connected to here. Where is the heat blanket? I forgot. I think this is the heat blanket, and then the other one is the vacuum. And then in this screen, you will program the temperature. It's like Windows 98 or something like that. It's really, really old school. This thing is, let's say 25K. But it's exactly like printers, that the printer is cheap and then they get you on cartridges. This is the same thing. There is a hidden cost here, and that's the heat blanket. Because for every geometry, for every condition, in the different heat blankets. So when I was in charge of buying these things, and I paid 25K for heat bonder, as it's called, and then I think I paid 100K for all the other, like we had like 50 heat blankets. Each of them was $2,000-$3,000. But you need it for different sizes, different powers, all stretchable, non-stretchable. There is another way of heating it up, which is through convection. So you can create a local oven, if you will. And then there's this big air blower that blows hot air. And this equipment can control this equipment as well. So you can either do by conduction with heat blankets, or you can do by convection using this, I forgot what they're called, heat blowers or what. This was $6,000. That was also cheap. So anyway, so as you can see, you're doing repair. So you will create, in this case, an enclosed section. It's not vacuum. The vacuum is probably under it. So it's like a vacuum part. And then above that, you're creating a local oven, if you will. Hot air comes in and heats up the enclosed area above the vacuum bag. And this thing receives signal from one of the thermocouples, perhaps, and then it can adjust the energy of the blower. That's how it works. So there are a couple of equipments. I think the famous one is heat bonder. Questions? We don't have this at UW, but I think we should definitely buy that. I'm thinking about buying one of those for my lab at some point. Okay, so the first strategy, you can take 3 heat blankets with different powers, and then, or 4 in this case, one here, one here, one here, and one there, and locally heat up with different powers. You can do that. It's a zonal heating. I forgot what it's called, multi-zone repairs. To do this, you need multiple equipment, right? So typically, each of these can control up to 2 areas. You can connect 2 heat blankets to this. I think one goes on one side, the other goes on the other side. Each side has its own thermocouples. But then if you have like, if you want to control an area with 8 different conditions, you need 8 of them. So the cost goes up. That's one thing. So network controllers, as it's called, is one way of mitigating the problem. This is what you said, Amir Ali. If you can have like specialized heat blankets. In this case, if you think about it, there is stringers, and then you have an area which is quite thick, an area which is thinner than that section. So you need more power in one area compared to the other one. So you will create these specialized heat blankets where there's more resistors in the size compared to the middle. But this adds to the cost. And also, if you think about it, there's, look at it, there's this basically sides to make sure you can apply vacuum on top of that. So this heat blanket is designed specifically for this geometry. So that's where the cost goes up. For every complex geometry, you have to have a very specific heat blanket. So variable watt density heat blankets is another solution, but adds to the cost. This is another one of those that, but you have to put multiple of these, and you can look at the shape of the area that you want to repair. So you need a very specialized heat blanket shape for that areas. And you have to have a manual for this aircraft that says for every damage scenario, how do you repair it? And it has to spill out. You have to have this type of heat blanket with this complexity or what, and you have to do the repair following this strategy. Then, like, I don't know, like, was it like an Alaska Airlines or an airliner? They have to have all of these heat blankets ready. So when the aircraft comes in, they can do the repair on them. There are stretchable heat blankets. Honestly, I don't know how they work. I have to go and look it up, but how do you heat up stretchable material uniformly? Or what's because there is no resistors. I don't know how they're doing it, but there are some. I don't know how well controlled if you stretch them too much or too little, but you can think about it. There's some cases, there's some geometries that is really difficult to do it any other way. So that becomes the only way of doing it. I've never used it myself, the stretchable heat blankets. I've always used the one that are non-stretchable. But then you need specialized heat blankets for curved surfaces, for example, for 3D geometry. And some of these are extremely expensive. So coming up with the entire tool that you need to maintain an aircraft is not an easy process. It's like you're doing manufacturing, local heating, non-uniform heating. I think one of the discussion topics today is about this. So you have to come up with a strategy that makes sense, time, quality, and expense. Okay. That's the last slide I had for today. Went too fast into all the slides. Any questions? Yes.
During the repair, my only concern is, right, we have a localized spot and then we're heating it. We're approaching the transition glass temperature to the surrounding part, right? How is that mitigated or controlled, that was?
Right. So good question. So some of the material that you're dealing with, they have really high glass transient temperatures. So what is the glass transient temperature? Let's say for material used in Boeing 787, it's around 220, 230 C. Okay. The curing temperature for that material is 180 C, let's say. If you are 25 C below glass transient temperature, is okay. It's not going to do anything to the aircraft. But it's a good point to consider. We have to consider the limitation of the material in repair. And if now that you're saying, if the temperature locally goes to 200 C, you're definitely getting close to that glass transient temperature. So it's a very dangerous zone to get close to. You might damage, you might create permanent deformation elsewhere, right? But some of the materials have low glass transient temperature. So that's like interiors, for example, if you're doing repair. So we have to be careful for those. I forgot one thing about the, now that I mentioned heat damage, how do you detect heat damage? I mean, here, discoloration, but if there was no discoloration, how do you detect heat damage? Do you know? So it locally changes the chemistry of the material, but maybe without like creating visual clue that it was heat. If you suspect an area is heat damage, handheld FTIR, yes. So there is a small handheld FTIR. I think every 787 has one of them on board, and they can go and locally inspect an area that suspect. I don't know. Imagine someone has like I don't know. If there's a small fire, if there's like I don't know, like a laptop catches fire or what, there's a side of the window that you suspect that there's damage, then you can do inspection right away. But it's only applicable to the surface, not the internal part. So you can only inspect the surface with handheld FTIR. Good. Thank you all. Give me back my samples, my failed attempt to make a company. It's only good for teaching now. Thank you, everyone.
How was that area inspected after